This particular packet is one of many that I have. So you're going to see, I think I have 8 or 9, maybe 10 different packets. In my room, I've got answer keys for these. So as you're going through them, if you want to check them to see if your answers are correct, I've got binders back there in the back of the room that have the answer keys in them. That is a helpful thing I've found in the past to allow students to kind of self-pace as they go through these reviews, and it won't be any different this year. So let's get into this. I'm going to put all my text in here in blue. At least I think I am. I'm going to make sure. Yeah. Okay, so I'm going to be putting my text in blue. I find that it helps me to find what I've written and pick out the answers more quickly if it's in a different color. Your mileage may vary. You can do what you want with it. But, you can follow along now, or you can work on it later, whatever you want to do. Not gonna, like I said, I'm not gonna make this like a class grade, but it will be part of your participation to see that these are finished. Okay, so not gonna really. I tried to do this morning with the third period class, asking them to kind of participate in these and fill in the blanks with me and discuss with me. They weren't really willing to discuss, and since I'm recording this, I think I'm just gonna go ahead and fill in the things and not ask you guys to throw in your responses, because I asked this top question: what are some sources of information that should be researched before experimentation? And it took like 3 minutes for anybody to even begin to answer. So I think in the interest of, getting through this, I'm just going to talk through them, kind of lecture style. So on we go. Standard 1, lab design and lab skills review. Again, as I said, it's really important. It's a big part of the Regents exam, and it doesn't hurt to know some of this material going into the world anyways. So when we're looking to come up with an explanation for something in the sciences, a lot of times we'll design an experiment around something. But before we do that, we try to come up with a prior explanation somebody else has given us. So generally speaking, these things are built on experiments based on our observations and inferences that we can make based on what we already know about the world. One of the things that we should do before we really begin an experiment, though, is go out and see if we can find, has anyone else already studied this, right? Has this been studied before? And so some of the sources you might want to look at are journals. You could look at websites, but we have to be careful with websites. The other things that you can look into are databases. And I don't know if you guys are aware of this, but our library has literally 100 different databases with all sorts of information. Stay away from, obviously biased websites when you're looking at scientific information, because a lot of people like to kind of put out the wrong stuff and gaslight people on these websites. When we move into learning about these scientific concepts or about the people who have contributed, it helps us to look at people who have done stuff in the past. Like, for example, as the example shows here, Lamarck proposed a theory of evolution based on his own observations and some thoughts that he put together. He felt that organisms that acquired characteristics during their lifetime, like, for example, if a person lifted a lot of weights and they got really strong and big muscles, they would pass that on to their offspring. Obviously, that's not the way it works. You can have a genetic predisposition to develop muscle mass, but for example, if I cut off my left arm and had children, my children would not be born without a left arm. So we know this theory doesn't really prove true in this case, but it still helped us in terms of science, because what it did was it provided a stepping stone for future exploration. So basically, every discovery uh, does this. You know, if you think about uh, cell phones and computers and things like that, um, they tend to increase our understanding, computers especially. As computer technology has improved over the years, our ability to improve computer technology has also improved. So it's kind of a positive feedback. And every step we take technologically leads us to more steps that we can get, take to get to something better. So Lamarck's work was essentially a base to work from, because he was one of the first people to really talk about how organisms became different over time. Values. When we look at this next one, this is how values entered into the fight over other groups or organizations having knowledge of a person's genetic profile. And so this is talking about taking genetic information and using it to make decisions about people and their potential and the risks of hiring them, for example. So this is kind of what we call a slippery slope argument. And what that means is, once you start going down it, it's hard to stop. For example, if we are looking at potentially not hiring someone because in their genetic profile they have a predisposition to cancer, and maybe that's not something you want to do. In fact, it isn't something you want to do, in my opinion. Because genetics is kind of, you know it's not terribly well understood yet how all the genetics works, and all the genetic components come together to create who you are. We don't fully understand how certain enzymes and proteins work together in our bodies yet. We're still working on some of that stuff. We have pretty solid knowledge of the human body, but not full. It's not by any stretch is it full. So ethical concerns are a part of this. So we have to kind of be careful when we talk about this. When we're looking for inquiry knowledge, we tend to start off with web searches. You can look in libraries, textbooks. Again, databases come into this. But one of the things about inquiry is that it's asking a question to try to solve a problem. And so it involves making judgments about sources and the relevance of the information, the value of the data that you have. And this goes back to kind of the reason why you really shouldn't take your scientific data from social media or like television commercials or whatever, because they may or may not be all that reliable, especially during election season, because we know that a lot of times politicians will create these attack ads to go after their political opponents, and they'll say a lot of things in them that are half true or barely half true or not even half true or complete falsehoods in some cases, just to try to smear their opponent so they can win. So the reason that I ask, why is it more important that we take information from a scientific journal, is one real reason, and that is because scientific journals are all peer reviewed, which means before they get published, other scientists review the research and make suggestions and corrections. So all scientific journals are peer reviewed. And in order to get a paper published in a scientific journal, you have to have you have to go through the peer review process, which can take months. You send your material out to, you know, X, Y, and Z, and they look it over and they make suggestions on your material, send it back to you, and then you can make corrections and improve your work. And then you send it back out. The end result is that when it, once you've gotten to the point where you're starting to collect data, you can start to talk about explanations for the phenomenon you're seeing. These things are typically accepted when the research and the experimentation is consistent, when the evidence and the data there support your conclusion, and when you can accurately predict what's going to happen in the next time that it's done. So the question here is, why must the explanation of an experiment correlate with the data obtained in the experiment? Well, that should be pretty obvious, I would think. The data should provide support for the conclusions being drawn. If they don't, then you're not really using the science the right way. The other thing here that's next is it says all scientific explanations are tentative and subject to change or improvement, and that's something I've talked about in class. We need to stay open-minded and stay willing to accept new information. And that's because, again, we never close the door on, even on something as fundamental as the law of gravity. For example, if I took this pencil and dropped it, it falls. On Earth, and basically every other known situation that I'm aware of, when you drop an object in a gravity situation, in an environment with gravity, that object will fall toward the most massive object around, and that happens in this case to be the Earth. But there may be a situation somewhere in the universe where that doesn't hold true, and so we leave that open for future exploration. So, it's kind of like we don't know everything about the natural world. So, okay. So we're going to leave things open for questioning. I'm going to move that text box up. It's kind of in the way. There. So we leave things open for further questioning. And it's important, because like I said before up above, every scientific discovery opens the door for more scientific discoveries, and we don't want to be closed-minded as scientists. We want to make sure that we're allowing room for improvement in all of these possible explanations that we come to. This right here is the definition of a theory. If it's an explanation that is supported by strong evidence, it's a theory. Okay. The difference between a theory and a hypothesis is the hypothesis has not been explained. A hypothesis is one possible explanation for something. It's not supported by evidence. It hasn't been tested yet. Well-accepted theories, these are the ones that have been around a long time. They have strong support from the scientific community, and they are clearly found to be true, well supported by many, many experiments over a long period of time. So that, that applies to the cell theory. We talked about it just a couple of days ago. Why is the cell theory accepted among most scientists? And that's pretty obvious. It's well supported by many experiments over many years. And this is, the work of Redi and Spallanzani and Pasteur and those things, that the people that were disproving the theory of spontaneous generation. So all of that kind of got disproved by these people, that were out there. I can turn the light on my camera, I think. That's better. Because my lights in my room just went off because I've been sitting still for 15 minutes, and that's no good. So These scientists disproved the idea that spontaneous generation could occur and could lead to the creation of new species or new individuals. So not new species, new individuals on the planet based on, you know, I don't know, they pop out of the air. I never really loved the idea of that particular thing, you know. Two methods that we can use to retrieve electronic information. Well, I mean, everybody's got one. You could use something like a cell phone, or you could use a computer. Um, those are two things you can use. So that's pretty obvious.
Couldn't you use a tablet too?
A what?
A tablet?
Sure. Tablet, whatever. Yeah. So this is going to lead us into the actual discussions about the scientific method now, and you know what we have been learning all throughout the year and various times, you know, and how we can design experiments that can be used to test different situations. But you always have to make sure you're aware of the safety procedures. You know, some of the obvious ones, you should wear eye protection. You know, you should tie back loose hair. You should wear closed-toed shoes. Know the chemicals you're working with. Let's see what else. Oh, a really big one, especially in my room most of the time, is make sure your workspace is clear. So all of these, you know, and there are other options you could put for this. Anything that makes sense you can put here. It doesn't really matter if you put something down here that isn't on this list. It's not going to be wrong. It's just different. You could put things like don't screw around, you know, pay attention, read the safety instructions, read the whole lab before you start it, that kind of thing. So all of these are fine. The next one is an intellectual prediction of the possible outcome of an experiment or a solution to the problem. And I would rather stop it right there. But, you know, the author of this particular packet added, this educated guess can only be made after a great deal of research, which to me seems like kind of an oxymoron. It's not really a guess if you're researching it, don't you think? So, you know, this is the definition of a hypothesis. I don't like calling it a guess. I really just don't. Because it's not. You're not guessing. You already know a little bit about it, and you're working from prior knowledge most of the time. So I don't like that definition. Correctly worded hypotheses, they need to be tested. They need to prove support. So they can be tested and supported using an experiment. Now, we want to make sure it's a controlled experiment, or things could go horribly wrong. So, you know, that's okay. The best way to write a hypothesis is really as an if-then statement. If Mr. Hunter turns up the heat in his room, then students will sweat. That is a fine hypothesis, and it is testable. It is repeatable. You could set that up anywhere you wanted and repeat it. So that, you know, that's what we want in a good hypothesis, an if-then statement. If you can manage it, you try to write them with an if-then statement. The if part is what we call the independent variable, and sometimes you'll also see it called the manipulated variable, but that terminology has kind of gone away. And then the then part leaves us with the dependent variable. And the difference between these, remember, is that independent, the researcher has control over. So you can choose what the independent variable is. The dependent variable, you don't have direct control over. It's changing in response to what you're doing with that independent variable. So the steps of a good controlled experiment, they all start with one thing, and that is observation. You have to make an observation in order to make an experiment. Then the next thing you're going to do is you're going to do a little bit of research, because nobody goes directly into the lab and sets up an experiment without looking it up first. It's just not done. And then after that, you design your experiment. Once you've done that, you can collect and analyze data, take that data and make some conclusions about it. And if you're happy with it, then the next thing you're going to do is repeat. And you're going to repeat, multiple times. So you want to try and go through a good experiment has been run multiple times, 20, 25, 30 times before it's accepted as kind of strong. Everybody's probably heard of bias. Bias is basically when the researcher's opinions change the way he looks at his data. So that's what's called a confirmation bias. There's a very famous one, and I'll talk about it here in just a second. But say you have a belief that a certain outcome is going to happen as a result of your experiment, and you are going to basically drive your experiment to reach that outcome. That is a confirmation bias. You're not setting it up to naturally reach that. So a bias is when a researcher believes in a certain outcome and sort of forces the experiment to go in that direction. So, in other words, ignores the data or falsifies it. This leads to an invalid experiment, obviously, but it can cause lots of problems. There's a very famous example of this, which again I'm going to get to in just a second. Anytime you increase trial size, trial number, or sample size, you increase validity. So because it tends to rule out the concept that it would be by random chance alone. Okay. If a hypothesis is incorrect, not a big deal. In fact, sometimes we set up hypotheses to be taken down. Sometimes they are exactly designed to be ruled out. So this is called a null hypothesis. Okay, so that's one. Sometimes a hypothesis is just you put it up there and say this is not the answer, but I'm gonna prove it through an experiment. It's also fine because if you're not seeing the support you want, a hypothesis can be restated. Okay, so if it doesn't support what you think it should, we can restate it and then run it again, and until we get it right. More trials, I just said this up there. More trials equals higher validity, greater. Oops. Why's my text box not forming? So the more information you have, the stronger your support is going to be. This is a thing you see a lot right now, and I don't love it. It leads to a circumstance called gaslighting, and you hear a lot about it now. But the main idea here with this is that all claims should be questioned, and fact and opinion should not really be intermingled in the statement of a claim. If you can't cite enough evidence, then you shouldn't conclude that a certain case is a fact. And this happens a lot, especially in politics. People say a lot of things, and they don't use evidence to back up their claims, and it drives me bananas because you see it on social media all the time. Facebook is an absolute nightmare of this kind of thing, where people make claims, but they don't have the data to support what they're trying to argue. And you know, as kind of, I don't know, we should have a stronger, in my opinion, a stronger argument if you do have a stronger argument if you have strong data supporting your point of view. There was one really famous example of this, and this is, I've been talking about it for a second now. There was a researcher who was convinced that vaccines caused autism. Okay, and so that was his opinion. So what he did was he set out and set up an experiment to prove that vaccines cause autism. And what he ended up doing was he falsified data and eventually got caught. His whole thing has been debunked, but a lot of damage was done to the, to the whole, basically to vaccine usage, because people began to believe this guy, because he's a famous scientist or whatever, and there's a whole movement about anti-vaccinations, and it was based on the fact that this guy went out and said vaccines cause autism, and it was not true. It's been thoroughly debunked, in fact. So I'm going to put that. I'm going to put that as my kind of example of this. But again, like I said, it caused a lot of harm. There have been a lot of people who refuse vaccines now because of what this guy said. It causes autism. It's not true. It doesn't. So here we have the next one. Results of an experiment need to be repeated. So you can't just do an experiment once and say, here we have it. This is the complete and total answer. It doesn't work like that. You've got to be able to repeat the experiment. If you can't repeat it, then it's no good. You designed it wrong. This goes back to what I said earlier, peer review. So, you send your results and your experiment out to other scientists, and they do all this. They analyze the procedures, examine the evidence, identify faults in your reasoning where you've made mistakes in the way you've looked at your data or falsified your data. Point out statements that are not supported by your claim or by your evidence, the claims that can't be supported by what you're saying. So you've gone too far based on the research that you did, and try to make suggest corrections and things so that the original author can go back and fix what they've done. They fine tune stuff this way.